Standard process control terminology. Purpose and role of standard control terminology defines uniform terminology in the process control and instrumentation field, facilitates efficient communication among industry professionals, helps in the understanding and interpretation of product specifications by users and vendors. History of Standards Organization. SAMA, Scientific Apparatus Makers Association. SAMA PMC 20.1 1973. Terminology associated with industrial process instrumentation and control. SAMA PMC 22.1 1981. Functional diagramming of instrument and control systems, including symbols and diagramming formats used in the process industry. ANSI, American National Standards Institute of ASME. ANSI C85.1-1963. Terminology for automatic control. Instrument Society of America. ISAS 51.1 1979. Process instrumentation terminology widely accepted in the process measurement and control industry. ISAS 5.1 Instrument Symbols and Identification, establishing uniform means for designating instruments and instrumentation systems. API, American Petroleum Institute. API RP 550, Manual on Installation of Refinery Instruments and Control Systems. Part 1, Process Instrumentation and Control. Part 2, Process Stream Analyzers. Part 3, Fired Heaters and Inert Gas Generators. Part 4, Steam Generators. Standard process control terms. Process, physical or chemical change of matter or conversion of energy, e.g., change in pressure, temperature, speed, electrical potential. Process control, regulation or manipulation of variables influencing a process to obtain a desired product quality and quantity efficiently. Input to process, mass or energy applied to the process. Output of process, the product delivered by the process. Supply, source of mass or energy input to the process. Control valve consists of the final actuator and controlling elements directly changing the manipulated variable. Load, anything affecting the controlled variable under a constant supply input. Open loop, control without feedback, cannot cope with load upsets. Primary element, the measuring element converting the measured variable into a form suitable for measurement. Transmitter, a transducer converting a measured variable into a standardized transmission signal. Controlled variable, the variable sensed to originate a feedback signal. Controller, a device operating automatically to regulate a controlled variable. Controller algorithm, PID, mathematical representation of the control action performed. Set point, input variable setting the desired value of the controlled variable. Error, algebraic difference between the real value and ideal value of the measured signal. Manipulated variable, quantity or condition varied as a function of the error signal to change the controlled variable. Feedback control, control action where a measured variable is compared to its desired value to produce an actuating error signal, reducing the magnitude of the error. Cascade control, control where the output of one controller is introduced as the set point for another controller. Feed-forward control, control action where information on conditions disturbing the controlled variable is converted into corrective action outside of any feedback loop. Continuous history of control. Instrumentation was initially used for monitoring or measuring purposes, with early examples in Roman times and Egypt. Manual control was common in the early 20th century, with operators walking through plants to adjust valves based on gauge readings. James Watt's flyball governor in 1775 was the first automatic control scheme using feedback control. The process industry emerged significantly during World War II, leading to the development of process instrumentation and control companies. Hardware-software evolution, 1930s. Mechanical hardware required direct connection to the process. 1940s. Pneumatic transmission allowed remote control and more sophisticated strategies like feed-forward control, but was limited by the speed of sound. 1950s. Electronic instrumentation, faster than pneumatics, allowed longer distance control and centralization of control rooms. Mid-1960s. Digital devices and computers were introduced, initially used with analog backup, evolving to direct digital control, DDC. Consequences of open-loop control. Open-loop control is effective only when the operator adjusts the valve. Any load change or supply upset affects product quality. Open-loop control cannot handle load variations and poses safety risks due to lack of regulatory control. Advantages of closed-loop control. Closed-loop automatic control offers economic benefits and safety improvements. Increased productivity maximizes the amount of products made in a process. On-spec products maintains product purity levels, avoiding off-spec production. Energy and material conservation minimizes material and energy use, optimizing control loops. Safety provides a first line of defense before emergency shutdown devices, ESD. Types of control. Continuous control, used in continuous processes with analog measurements and digital controllers, maintaining process values despite disturbances. Sequential, on-off control involving a series of discrete actions in a specific order, used in valve lineup sequencing and pump compressor startup shutdown. Batch, combination of sequential and continuous control with time-dependent, repeatable operations used for blending and transfer operations. Determining controller action required for negative feedback. Positive feedback. Positive feedback in a closed loop reinforces the error until a limit is reached. Example, a tank's level control where exceeding the set point increases the level further until overflow. Positive feedback must be avoided as it leads to instability and undesirable outcomes. Negative feedback. Negative feedback in a closed loop minimizes the error depending on the controller's algorithm. Example, a tank's level control where exceeding the set point reduces the level. Essential for all automatic feedback loops to ensure stable and desired control outcomes. Direct acting element. An element where the output signal increases with an increase in the input signal. Input and output signals move in the same direction. Reverse acting element. An element where the output signal decreases with an increase in the input signal. Input and output signals move in opposite directions. Elements in series. When elements are combined in a control loop, their overall action determines the loop's feedback type. Direct acting elements in series maintain the direction of the input-output relationship. Reverse acting elements in series change the direction, affecting the overall loop behavior. Control valves. The primary flow controlling element in a process control system. The valve's input is the stem position, while the output is the flow. Common household valves, faucets, are typically direct-acting valves, where increasing the stem position increases the flow. Valve plugs. Valve plugs can be direct or reverse-acting. Direct-acting plug, flow increases with the stem position. Reverse-acting plug, flow decreases with the stem position. Pneumatic valve actuators and plugs. Most common valve type is air-operated pneumatic valves. Air to open, ATO valve. Air pressure opens the valve, fails closed if air supply fails. Air to close valve. Air pressure closes the valve, fails open if air supply fails. Valve positioners can also achieve direct or reverse action. Transmitters. Transmitters convert the measured variable into a standardized transmission signal. Can be set up as direct acting, output increases with input, or reverse acting, output decreases with input. Most transmitters are direct acting. Processes. Processes can be direct or reverse acting. Energy flow process, heat exchanger. Direct acting, steam flow increases temperature. Refrigeration, reverse acting, refrigerant flow decreases temperature. Mass flow process, level tank, direct acting, flow input increases level. Pipe flow, reverse acting, flow increases, suction pressure decreases. Select control action per application. Controller action is selected based on the action of other elements in the loop to achieve negative feedback. Error calculation can be done as reverse action, E equals R minus C, or direct action, E equals C minus R. Rule for achieving negative feedback: must have an odd number of reverse acting elements in the loop. Additional benefits of open loop data. Open loop tests help determine the combined effect of elements and the required controller action. Data obtained from open-loop tests provides process characteristics and helps calculate preliminary PID settings. Identifying acceptable negative feedback loop responses. Loop gain and loop response. Dynamic responses depend on the total loop gain vector of the open loop, which includes magnitude and phase. Gain of an element is defined as the ratio of change in output to the change in input. Steady-state gain K. Ratio of output amplitude to input amplitude when both are time invariant. It is a scalar value without an associated phase shift. Magnitude of total gain vector, Kg or G. Ratio of output amplitude to input amplitude when the input signal is sinusoidal. Involves both magnitude and direction. Total gain vector, G. Calculated as the ratio of the derivative of the output to the derivative of the input. Represented as G equals d dt output, d dt input. Phase shift F. The difference in phase between the input and output signals. Can be a phase lead, positive angle, or a phase lag, negative angle. Dynamic response based on the gain function. Loop gain is the product of the gain functions of all loop components, transmitter, controller, valve, and process. Oscillatory response occurs if the phase shift around the loop is 360 degrees or a multiple of it. The loop gain values determine the type of dynamic response. Overdamped, critically damped, underdamped, constant amplitude cycling, or increasing oscillation. Dynamic response as a function of loop phase shift. Oscillatory response requires a -360-degree phase shift around the loop. If the phase shift is less than 360 degrees, the loop will have a damped response and eventually stabilize. The control algorithm contributes to the phase shift and overall dynamic response of the loop. Work Aid 1, procedure for determining required controller action for negative feedback. Rule: an odd number of reverse-acting elements are required for negative feedback. Procedure involves putting an input on each element, observing the output, and recording the action. Work Aid 2, identification summary of acceptable negative feedback response types. Acceptable responses: overdamped, critically damped, underdamped, quarter amplitude decay. Unacceptable responses: constant amplitude cycling, increasing oscillation. Explaining the general selection considerations for process instrumentation. Selection considerations for process instrumentation. Reliability: probability that a component, piece of equipment, or system will perform its intended function for a specified period without requiring corrective maintenance. Accuracy: degree of conformity of an indicated value to a recognized accepted standard value or ideal value. Measured accuracy includes the maximum positive and negative deviation observed in testing a device under specified conditions and by a specified procedure. Accuracy rating includes conformity, hysteresis, deadband, and repeatability errors. Precision and bias errors. Accuracy error is the sum of precision error and bias error. Precision relates to the ability of a measuring device to repeat the same reading for the same input. Bias is the difference between the true value and the instrument's most likely reading, which can be calculated and corrected. Other selection considerations. Primary elements, transmitters, range, the region between the limits within which a quantity is measured. Span, the algebraic difference between the upper and lower range values. Minimum and maximum span, the range within which the primary element can measure accurately. Rangeability turndown, the ratio of maximum flow rate to minimum flow rate within the stated accuracy rating. Zero elevation and suppression, the range at which the zero value of the measured variable is not at the lower range value. Response time, the output as a function of time resulting from a specified input. Faster response times are preferred. Time constant, the time required for a first-order system to reach 63.2% of the total change when forced by a step input. Characteristic curve input-output relationship shows the output variable as a function of an input variable, affecting overall loop linearity. Reproducibility, closeness of agreement among repeated measurements of the output for the same input. Noise, unwanted components of a signal or process variable, which should be minimized to acceptable levels. Identifying the most commonly used transmitters. Role of transmitters. Transmitters convert process variable measurements into standardized signals suitable for transmission and control. Centralizes control operations by transmitting signals over long distances, avoiding hazardous conditions and response time issues associated with original measurement forms. Transmitter types. Pneumatic transmitters use air pressure to transmit signals. Electronic transmitters convert process variable measurements into electronic signals. Digital transmitters use digital signals for improved accuracy and additional capabilities, such as remote calibration and diagnostics. Smart transmitters, microprocessor-based, allowing remote calibration checks, self-diagnostics, configuration, and rearranging. Transmitter components. Detector detects the process signal input or primary element output. Amplifier amplifies the detected signal. Negative feedback balances and stabilizes the mechanism to accept changes in the primary element's output. Simplified transmitter schematics. Pneumatic type, simplified schematic showing the conversion of process signal input into an air pressure output. Electronic type, simplified schematic showing the conversion of process signal input into an electronic output. Resonant wire type, uses wire tension changes to affect the resonant frequency of an oscillator circuit, converting pressure changes into frequency changes. Transmitter calibration. Calibration adjusts the transmitter to ensure accurate signal output corresponding to the measured variable's input. Zero adjustment ensures that at 0% measurement input, the output is also 0%. Span adjustment ensures that at 100% measurement input, the output is 100%. Calibration involves iterative adjustments to ensure linearity and accuracy across the entire measurement range. Gain of transmitters. Gain is a measure of how much the transmitter's output changes in response to a change in input. Transmitters are generally fast-acting devices with minimal dynamic gain concerns. Changes in measurement span or recalibration can affect the transmitter's gain, impacting overall loop stability and performance. Describing the most common final control elements used in process applications. Control valve terminology. Control valves are engineered variable flow restrictions used to maintain desired values of flow rate, pressure, temperature, liquid level, and composition in a process. Input signal to the control valve is the output signal from a controller, which determines the stem lift and the area open for flow. Valve body types. Linear actuated valves. Globe styles, conventional globe type, single-seated, and double-seated valves. Single-seated valves provide tight shutoff, used in small sizes, and where unbalanced forces are unimportant. Double-seated valves reduce required actuator forces due to balanced hydrostatic effects, but have higher leakage rates. Globe-style three-way valves, used for diverting or mixing services. Angle valves, single-seated valves used for specific piping designs, preventing solids accumulation and handling erosive fluids. Rotary actuated valves. Cage valves, most often specified due to economic and performance advantages, easy maintenance, and trim removal. Butterfly valves, used for low to moderate pressures and large flows, featuring elastomer inserts for tight seals. Ball valves, use a spherical plug to control fluid flow, suitable for high-capacity flows with tight shutoff capability. Eccentric plug-type ball valves, characterized by an eccentric path for the plug, suitable for erosive materials, providing high rangeability. Control valve application considerations. Material and connections. Selection based on application, operating conditions, and economic considerations. Valve trim and actuator size determines the valve's capacity and suitability for specific applications. Noise level and fail-safe considerations. Ensures operational safety and effectiveness during power failures. Flow characteristics. Inherent flow characteristic, ideal flow characteristic under constant pressure, drop characteristic. Actual input-output characteristic of the valve, affected by operating conditions. Rangeability, turn down, ratio of maximum controllable flow to minimum controllable flow, indicating when it is safe to switch to automatic operation. Dynamic considerations. Speed of response, stroking speed, and power loss considerations to ensure effective control loop performance. Fail-safe consideration determines the valve's behavior during air supply failure to ensure safety. By understanding these elements, appropriate control valves and their configurations can be selected to achieve desired process control and performance. Identifying other control loop elements and their roles. Signal converters. Current to pressure signal converters, IP, convert electronic signals to pneumatic signals for valve actuators, typically mounted close to the valve to minimize transmission lag. Pressure to current signal converters, PI, convert pneumatic signals to electronic signals for longer transmission distances and reduced lag. Commonly used for integrating with electronic recorders, indicators, and computers. Analog to digital, AD, or digital to analog, DA converters. Convert analog signals to digital signals and vice versa in digital or computer applications, used in direct digital control, DDC systems to handle multiple control loops. Volume booster, a pneumatic device that acts as an isolating amplifier, increasing the volume or pressure of air, used to extend signal transmission distances and improve valve response time by charging valve actuators more quickly. Helps isolate controllers from large capacitive loads of actuators. Valve positioner, a proportional-only controller that eliminates or minimizes valve hysteresis caused by valve packing, plug seals, and other factors. Enhances valve performance by ensuring accurate valve stem positioning as dictated by the control signal. Additional functions: provides tighter shutoff by increasing actuator loading pressure. Acts as a volume booster to improve dynamic response for large actuators. Converts current signals to pneumatic signals, IP function. Characterizes valve output through cams or other means, changing valve characteristics. Alters valve action from direct to reverse and vice versa. Enables valve sequencing, split ranging for extended rangeability. Valve sequencing split ranging, a control strategy where a controller's output actuates more than one valve to achieve higher rangeability. Valves are calibrated to operate in specific portions of their range, ensuring smooth transition and extended control range. Ensures that only one valve operates at a time, with logic provided to manage transitions between valves. By incorporating these control loop elements, the overall control system can achieve better performance, accuracy, and responsiveness tailored to the specific requirements of the process.